Every time you stream a movie or share a photo or even just click save on a cloud doc, you're tapping into this massive, totally invisible world. It's this hidden universe of humming servers and blinking lights, all whirring along in these super controlled environments. And that's the backbone of our digital lives. So today, we're going to pull back the curtain on this unseen engine that powers everything, the modern data center.
So, here's how we're going to break it down. We've got 5 parts to our journey. First, we'll tackle the biggest challenge of all, the power problem. Then, we'll see how you go from just an idea to a full-blown blueprint. After that, we'll dive into the actual hardware that makes up the machine. Then, we'll explore the crazy complex systems that power and cool the whole thing. And finally, we'll see how it's all managed 24/7 to keep our digital world up and running.
All right, let's dive right into part 1, the invisible engine room. And the central theme here, the one problem that drives literally every single decision in data center design, is its incredible, almost bottomless appetite for power. I mean, it feels instant, right? You just click. But what really happens? Well, that one little action kicks off this incredible chain reaction. Your data zips through networks to a real physical building, could be hundreds, even thousands of miles away. It gets written onto a storage device, which is inside a server, sitting on a rock, that's getting a constant stream of super clean power and being blasted with chilled air. That one click, it uses real physical stuff. So what exactly is a data center? I mean, officially. It's so much more than just a room full of computers. Think of it as a purpose-built fortress. You've got all the IT gear, right? The servers, the storage, the networking stuff. But just as important, maybe even more important, is all the support infrastructure. We're talking massive power systems, complex cooling, top-notch security, all of it working together for one single mission, to make sure that IT gear never, ever turns off. And this is really the heart of the whole problem. We are not talking about just a little extra power here. Data centers are some of the most energy-hungry buildings on the entire planet. A single large facility can easily consume as much electricity as a small city. This incredible power draw is the central challenge that engineers and designers spend their entire careers trying to solve. And here's where all that energy goes. Check it out. Over half of it goes straight to the IT equipment itself. But look at the second biggest slice, cooling, at a massive 30%. This is the key relationship you have to understand. Every single watt of power that goes into a server comes out as heat, and that heat has to be removed. So the more power your IT uses, the more power your cooling system needs. That's the core efficiency challenge right there.
Which brings us right to part 2, from idea to blueprint. Look, if you want to build an efficient, reliable data center, you can't just start buying servers and plugging them in. It takes meticulous, upfront planning. The best analogy is building a Formula One car. You spend months and months in design and simulation before you ever cut a single piece of carbon fiber. This is that phase.
And this quote from Carnegie Mellon's Software Engineering Institute just hits the nail on the head. It perfectly captures why this is so critical. Almost any problem that pops up after the concrete is poured and the racks are bolted down can be traced back to a mistake made right here in the planning stage. One little oversight here can lead to millions of dollars in wasted energy or incredibly expensive fixes down the road. So the planning process follows this really logical path. You start at the very highest level by figuring out the design drivers, the big picture goals. From there, you translate those goals into specific user and system requirements. It's only then that you evaluate the physical space to see if it can even support those needs. And finally, with all that info in hand, you can actually start to design the infrastructure. These design drivers are basically the North Star for the entire project. They usually fall into 3 main buckets. First, functionality. What does this thing actually have to do? Second, constraints. These are your hard limits, the budget, the location, any regulations you have to follow. And third, the growth plan. You're not just building for today, you're building for 3, 5, maybe even 10 years down the line. And this table is a great example of how those high-level drivers get turned into a real concrete checklist. Big abstract goals like security or capacity become very specific questions about things like badge readers and what kind of data you're storing. Answering these questions is what turns a vague idea into a workable blueprint. Okay, the plan is locked in. So now we move to part 3, building the efficient machine. This is where we get into the actual hardware. We're going to start with the heart of the data center, the servers and storage. And then we'll tackle the single biggest challenge they create, getting rid of all that heat. In our F1 car analogy, this is the engine and the aerodynamics. So here is the most crucial point. If you want an efficient data center, you absolutely have to start with efficient IT gear. Remember that cascading effect we talked about? Every single watt you save at the server level is a watt you don't have to provide with power infrastructure, and it's a watt of heat you don't have to remove with the cooling system. Starting here creates this amazing ripple effect of savings across the entire facility. And one of the most direct ways to do this is by choosing high-efficiency servers. Programs like Energy Star set a really high bar for performance. A server that meets these top requirements is going to be, on average, about 30% more efficient than a standard one. This single purchasing decision can dramatically lower the baseline energy use of the entire place. And what's really fascinating here is that efficiency isn't just about what you buy, it's about how you use it. Look at this chart. A power supply isn't most efficient when it's barely working or when it's maxed out at 100%. No way. It has this perfect sweet spot, usually somewhere between 40 and 60% load. This is why right-sizing is so critical. If you buy a massive oversized power supply and it's just coasting along at a low load, it's just incredibly wasteful. You've got to match the machine to the job. Now, the next huge leap forward in IT efficiency came from something called virtualization. For decades, the model was basically one application per server, which meant most of your servers were just sitting there, idling and wasting power. Virtualization totally changed the game. It lets you run dozens of virtual servers on a single physical machine, which drives your utilization way, way up. You get the same amount of work done with a fraction of the hardware, power, and cooling. It's a game changer. Okay, so we've picked efficient servers, we've consolidated our workloads through virtualization. We've basically done everything we can to reduce the energy going in. Now we have to deal with the inevitable result, all the heat coming out. And this brings us to the world of air management. The absolute foundation of modern data center cooling is the hot aisle, cold aisle layout. It's a really elegant, simple idea. You just arrange your server racks so all the cold air intakes face each other. That's your cold aisle. And all the hot air exhausts face each other on the other side, your hot aisle. The goal is brutally simple. Don't let the hot and cold air mix. But to make that layout really work, you have to be obsessive about the details. Every single little gap allows that air to mix and waste energy. That means using what are called blanking panels to cover up empty slots, sealing up every cable opening, and even using containment systems, like plastic curtains or doors, to completely isolate the aisles from each other. Even messy cables can create hotspots. Every detail matters. Okay, here's a number that surprises almost everyone. We all have this image of data centers as these meat lockers, right? Super chilly, like 65 degrees. Well, not anymore. Modern gear is built to run way warmer. The recommended upper limit from ASHRAE is actually 80.6 degrees Fahrenheit. That's 27 Celsius. And letting the data center run warmer like that, it dramatically slashes the energy you need for cooling. Seriously, every single degree you can raise the temperature saves a ton of money. This leads us perfectly into part 4, powering it all smartly. Now we're getting into the real heavy machinery, the chillers, the pumps, the massive electrical systems that act as the life support for all that IT gear. For decades, we've cooled data centers with air, and it works fine, but it has its limits. As servers get more and more power dense, especially with things like GPUs for AI, we're literally reaching the physical limits of what air can cool effectively. The future? The solution is direct liquid cooling. Water and other fluids are just way, way better at absorbing and moving heat, which makes this the technology for high-performance computing. And this direct liquid cooling comes in a few different flavors. You have things like a rear door heat exchanger, which is basically like putting a car's radiator on the back of the server rack. You can take it a step further with cold plates, which attach a liquid-filled block directly onto the hottest parts, like the CPU. And then you have immersion cooling, the ultimate solution, where you literally submerge the entire server into a tank of non-conductive fluid. Now, regardless of the cooling method, one of the biggest opportunities for savings is something called free cooling. It's a simple idea. Instead of running your massive energy-guzzling chillers, you just use the cool outside air or water to do the work. And this connects right back to running the data center warmer. The warmer your data center can operate, the more hours per year the outside temperature is cool enough to provide you with that free cooling. So, cooling is half the battle. The other half is power. And it's not enough for the power to just be on. It has to be perfectly clean, incredibly stable, and completely, totally uninterrupted. 24 hours a day, 7 days a week, 365 days a year. No exceptions. The first line of defense against any power problem is the uninterruptible power supply, or UPS. The easiest way to think about it is as a giant, incredibly sophisticated battery backup. If the power from the utility ever fails, the UPS takes over instantly and seamlessly, providing power for those crucial few moments it takes for massive backup generators to roar to life and take on the full load. And here's where tiny little efficiency gains have a huge impact. This number, $90,000, is the estimated annual savings for a medium-sized data center just by improving its UPS efficiency by 5%, just going from 90% to 95%. That little difference means less wasted energy, a lower power bill, and less heat you have to get rid of. In a system that runs 24/7, that adds up incredibly fast. Okay, we've spent all this time talking about getting rid of heat as efficiently as possible. But here's a really cool, forward-thinking question. What if that heat, the data center's biggest waste product, could actually be turned into a valuable resource? The crucial point here isn't just the heat, it's the quality of the heat. See, low-grade heat isn't very useful. But when a data center runs warmer, the waste heat it produces is at a higher temperature, and that makes it valuable. This high-quality heat can actually be captured to warm up office buildings or even entire neighborhoods, turning a major liability into a real asset. And this brings us to our final section, Part 5, the constant checkup. A data center isn't something you just build and then forget about. It's a living, breathing system that requires constant monitoring and tweaking. For our F1 car, this is the race day telemetry, where you're tracking every single variable to squeeze out every last bit of performance. This old business saying is basically the mantra of data center operations. If you want to improve efficiency, you have to collect data on everything, from power consumption to airflow to temperature. Without hard numbers, you're just guessing. And that's why benchmarks and key performance indicators, or KPIs, are so essential. By far, the most widely used metric in the industry is power usage effectiveness, or PUE. It's a pretty simple ratio. You take the total energy the facility uses and divide it by the energy used by just the IT equipment. A perfect PUE would be 1.0, which would mean zero overhead for coolant or power distribution. Of course, that's impossible, but the goal is always to get as close to 1.0 as you can. And this chart gives you a pretty good sense of what those PUE numbers mean in the real world. The industry average is somewhere around 1.55. A score of 1.4 is considered pretty good, and if you're getting down near 1.1, well, that's considered world-class. This one single number lets operators see how they stack up against the rest of the industry and track their own improvements over time. But while PUE is kind of the star of the show, it's not the only metric out there. A whole family of these effectiveness metrics has popped up to give a much more complete picture of a data center sustainability. There are metrics for energy reuse, water use, even carbon use, giving you a complete dashboard of its environmental impact. Now, efficiency is crucial, but it means absolutely nothing if the data isn't safe. The number one prime directive of any data center is to protect the data and ensure things keep running. So beyond efficiency, the facility has to be resilient, and the absolute cornerstone of that resilience is a rock-solid data backup plan. A widely adopted and incredibly effective strategy for protecting data is known as the 3-2-1 backup rule. It's a simple framework, but it's designed to protect your data from pretty much any failure you can imagine, from a single hard drive dying to a natural disaster that takes out the entire building. It's really clever. So let's break it down. It's simple. The 3 means you need to have 3 total copies of your data. That's your original live data plus 2 backups. The 2 means you store those copies on 2 different types of media. Why? Because you don't want one single point of failure. So maybe one is on a hard disk array and the other is on tape. And the one, this is the big one, you keep one of those copies completely off-site. That's your ace in the hole, your ultimate protection against a total disaster like a fire or a flood at your main location. And that brings us to our final question. We've gone on this whole journey from a simple concept to these incredibly complex operations. We've seen the amazing engineering that goes into making these places more efficient and resilient. But the fundamental challenge still remains. As our world becomes more and more digital, how do we build a truly sustainable infrastructure, one that can power the future we all want, without draining the resources of the present?